Through this project, we were faced with several problems, all relating to the creation of 4-bar mechanisms in MATLAB. The scripts that we had to design needed to be able to show the range of motion for the following linkages and a couple of curves: the crank rocker, double crank, and as well as this, we also had to give more in-depth information about the mechanisms such as the Grashof type and whether or not the linkage is physically possible. The project specifically calls for the design and animation of an approximated level luffing crane. This needed to show the coupler motion with as close to horizontal linear motion as possible, whilst calculating the joint angles. Grashof's rule separates the linkages into two categories, type 1 and type 2. And the classification process is as follows. If the linkage satisfies Grashof's rule, then it is known as a Grashof type 1. This means that two joints are able to perform complete revolutions and two are able to oscillate between the motion limits. If Grashof's rule is not satisfied, then the linkage is known as a Grashof type 2. This implies that no joint can perform a complete revolution and all joints oscillate between the motion limits. Type 1 Grashof links are further separated into three categories: 1.1, 1.2, and 1.3. 1.1, also known as a crank rocker, is where the shortest length, S, is connected to the ground but not explicitly the ground link. The joint between length S and the ground perform a complete revolution. 2, also known as a double crank, occurs when the shortest length S is explicitly the ground link. Both of the ground links on this linkage can perform full revolutions, thus the name double crank. 1.3 is also known as a double rocker and is created when the shortest length S is the coupler link. Under this configuration, neither of the ground joints undergo full rotation. In addition to this, the motion limits were determined using the motion limits diagram provided in the unit reader as shown. The diagram outlines motion limits for specific 4-bar linkages. Finding the motion limits allows the position of a 4-bar linkage to be analysed over the range of motion. Code was based on the pseudocode and the course reader mathematic equations. First step was to create the input interface, second step was to create the Grashof analysis scripts, third step was to create the motion limits and error messaging, and the fourth step was to create the coupler curves and linkage calculation scripts. Despite this, we still had issues with tracing curves, plotting impossible linkages, and also with complex numbers ruining our script. Whilst we had minor issues with impossible angles and subsequent output error codes, and also with input specification issues, our main problem was tracing the coupler curve. We were unable to make the trace and animation occur on the same axes, and to circumvent this, we decided to put two sets of axes, one with the animation and one with the trace. Another major issue was that we could not produce linkages with a θ1 value other than 0. This is related to the occurrence of complex numbers in our calculations for θ4 due to the square root in the equation. This did not prove to be a fatal error, however, as our luffing crane was designed with a θ value of 0. Our final code now shows all required specifications, and will fail when it's an impossible linkage. Our initial code had issues with scale, with drawing the coupler curves, as well as with producing impossible angles. Through trial and error, we found that these were the best linkage lengths for the respective linkage types, and are shown using our final code in the next set of animations. Though the coupler tracing was initially an issue, our final code has the benefit of separate axes where the animation of the linkage and the coupler curve do not impede one another. For the luffing crane section, we needed to determine the dimensions and approximation of a level luffing crane, trace a coupler point with a linear horizontal motion, and calculate the linkage lengths, joint angles, and motion limits. The level luffing crane is a special type of double rocker with an extended coupler link as per design specifications. Our preliminary designs were conducted on GeoGebra, and our preliminary inputs are as shown. Significant experimentation, our final lengths are as shown. This gave us satisfactory crane movement and is shown in the animation as follows. Though there were issues with the input interface, coupler trace and motion limit algorithm coding, we feel that our grasp of the mathematical concepts as well as our final product, that being a working level luffing crane and a strong and visually appealing output, more than satisfy the requirements of the project.